My name is Jingwei Yi. I'm assistant professor at Louisiana State University. I'll be presenting our paper on polarimetric Helmholtz Stereopsis. This work is done with my student Yu Qiding and our collaborators Yu Ji, Mingyuan Zhou from Dijing, and Xinbin Kong from Zillow Group. Our proposed method uses the reciprocity of polarized light for 3D reconstruction. It can recover high-quality surface geometry with a few reciprocal polarization images. We all know that the light path is reversible, which means that when the lighting direction is reversed, the light follows the same path to go back. This property of light is called Helmholtz reciprocity, as it was first described by the German physicist Hermann von Helmholtz in his book Physiological Optics, published in the 1850s. This theorem implies the reciprocity of surface reflectance. When modeled with the bidirectional reflectance distribution function, or BRDF, the BRDF value remains the same when evaluated at interchangeable viewing and lighting directions. Using this property, Ziegler et al. Proposed the Helmholtz Stereopsis that estimates the surface normal from reciprocal image pairs. The pair is taken by switching the camera and light source positions. As the BRDF is symmetric under this setting, it can be cancelled out by dividing the intensity of the two images. For this reason, this method is independent to surface reflectance, but it requires at least 3 pairs to solve the normal. Here we extend the problem by considering polarized light. The central questions that we are trying to answer here are: does polarimetric BRDF still follow the same reciprocity principle as the intensity-based one? And can we perform Helmholtz stereopsis with polarized light? The original theorem of Helmholtz reciprocity had reference to the polarized light, and it has constraint on these references. The reciprocity principle only holds when the references are associated with the path. Here I show such an example. However, this constraint can hardly be satisfied in reality. In a practical scenario where a light source and camera are used to form the reciprocal path, the polarization of the path segments are represented under their own local references. In this setting, the original Helmholtz reciprocity cannot be directly applied to characterize the polarimetric BRDF. Here we derive the reciprocity relationship of polarimetric BRDF in general. We consider a pair of reciprocal paths with polarized light. The polarization states are determined under local references. We use the Stokes vector S to represent polarization states and the 4x4 Miller matrix M to represent polarimetric BRDF. Our goal is to derive the reciprocity property of M when it's evaluated with reciprocal path. In order to apply the original Helmholtz theorem, we define a global reference that is associated with the path, such that it satisfies the constraint of the original Helmholtz theorem. Therefore, the polarimetric BRDF M' that is computed under this setting obeys the reciprocity principle. By rotating the polarization references back to the local ones and comparing the two equations highlighted in yellow, we show that the value of M has a transpositional relationship. So we conclude that a reciprocity relationship for polarized light in general can be expressed as the transposition of the Miller matrix M. By applying this transpositional reciprocity, we can derive constraints for depth and normal estimation. Assuming linearly polarized light, we form the reciprocal pair by switching the camera and light source positions. We formulate the Stokes vectors that arrives at the camera by taking the product of light source Stokes, the polarimetric BRDF, and the distance and angular falloff vectors. By applying the transpositional reciprocity, we can eliminate the BRDF term in the equations. We thus obtain the reciprocity constraint that allow us to compute the surface normal from reciprocal image pairs. With this constraint, the minimal number of pairs for normal estimation is 2. By comparison, the standard Helmholtz stereopsis requires at least 3 pairs. As the polarization of reflected light is directly related to surface geometry, we can further reduce the minimum requirement of reciprocal image pairs by incorporating polarimetric constraint that correlates the angle of polarization with surface normal. As the angle of polarization varies across different types of reflectance, we propose the new image decomposition method that separates a polarization image into 3 components based on the polarization type and reflectance type. Specifically, our decomposition method takes in 2 sets of polarization images captured under orthogonal linear polarized light. We convert the polarization images into the Stokes representation that indicate the image intensity and polarization preferences. We first compute the diffuse polarized component by adding the input Stokes. As 2 inputs are captured under orthogonal polarized light, adding them together cancels out the specular component. Next, we compute a specular polarized component by subtracting the diffuse polarized Stokes from the input. For both components, we can compute the intensity image S0 by adding up S1 and S2, following the Stokes factor constraint. Finally, we compute the intensity of the diffuse unpolarized component by subtracting intensities of both specular and diffuse polarized ones from the input. The angle of polarization, or AOP, are used as constraints for normal estimation. We formulate our polarimetric constraint using the AOP from the diffuse polarized component. Here we show the decomposition results on various objects. We compare the AOP map for our diffuse polarized component versus the AOP from the overall input. We can see that the diffuse AOP map is more accurate and informative, as it reveals more angle variations. Finally, by combining the reciprocity and polarimetric constraints, we only need 1 reciprocal pair to estimate depths and normal. We can form a linear system about the normal M. The coefficient matrix W is a function of the depth D. In order to have a single solution, the rank of W should be 2. We then use this rank constraint for depth estimation. Given the optimal depths, we can solve for the normal with the linear system. We iteratively refine the depths and normal estimations for better accuracy. We first validate our method on synthetic data. We use the Mitsuba 2 renderer to simulate polarimetric images, and we test on various reflectance in real captured highest PBRDF dataset. We simulate images as captured by a polarization camera. For each pixel, we have 4 measurements at different polarization angles. We simulate 2 reciprocal image pairs, and at each viewpoint, we render images under horizontal and vertical linear polarized light. Here we show our normal reconstruction result using 2 reciprocal pairs. From the angular arrow map, we can see that our recovered normals are highly accurate. Here is the surface reconstruction result. Here are more synthetic results performed on objects with various materials. We can see that our method is robust for different types of reflectance. We also perform real experiments for validation. We build a prototype system that uses a rotating wheel to precisely exchange the camera and light source positions. We use a polarization camera to capture the polarimetric image in 1 shot. And we use a point light source with motorized linear polarizer to produce horizontally and vertically polarized lighting. To capture a reciprocal pair, we rotate the wheel by 180 degrees. At each position in a pair, we capture 2 polarization images under orthogonal polarized lighting by turning the light source polarizer. We quantitatively evaluate our method by reconstructing a billiard ball with known diameter. We compare the normal map from the standard Helmholtz Stereopsis that is done with 3 pairs with our 1 pair and 2 pair results. Our 1 pair result has large errors at oblique polarization angles because the polarimetric constraint becomes unstable at these places. However, the mean angular error is still smaller than the standard Helmholtz Stereopsis with 3 pairs. Our 2 pair result is highly accurate. Here we show the cross-section comparison of recovered surface profiles. You can see that Both our 1-pair and 2-pair results are closer to the ground truth than the standard approach. We then test on this orange seam and compare our 2-pair reconstruction result against several classical 3D reconstruction methods, including photometric stereo, shape-form polarization, and structured light. We can see that our results appear to be more accurate with better surface details. Here we show the normal and surface reconstruction result of a complex seam with composite materials. You can see that both types of surfaces are well recovered. In particular, the fine geometric details on the bandage are very well preserved in our reconstruction. Here are more reconstruction results on real seams. All these results are computed with 2 reciprocal pairs. Here we show some failure examples. Our method doesn't work well in presence of strong inner reflection because it causes caustics on the surface. Our method also fails in transparent areas where transmission is dominant. In summary, we extend Helmholtz Stereopsis with polarized light and derive a transpositional reciprocity relationship for polarimetric BRDF under general conditions. With the polarization information, our method reduces the number of reciprocal pairs needed for 3D reconstruction. Our method can recover various types of surfaces with good accuracy. However, our system has limitation on handling strong interreflection and transparent scenes. Thank you for watching our presentation. Please visit our website for more details.